Oh, hi. I'm Mr. Precella, and
I'm Mr. Precella. Where am I looking?
right
Am I
here.
looking right?
Yeah, you're looking correctly. Okay. Well, anyway, we're going to discuss inverse functions today. And we can close off this camera now. You've seen it. Let's see. Hey, this is one of those where it isn't making you click on every...
You still got to click. Remember, you still got to click on every one of them if you want credit for the problem, okay? You don't have to watch it. Just click it until you get the little
green
check.
Okay,
Or
so
if
we
you have
already
to
have a
watch.
21 on it. Okay, good.
Okay.
So if you don't click on these things, you're not going to make...
100, no
well, you
matter
can't make
what.
an 80.
You're right.
Okay. Okay.
And I want to remind y'all of something we saw a while back. Remember, I said...
Show it to us.
I said a function is a rule that assigns to each x value exactly one y value. The domain is a set of all x values. The range is a set of all y values. And we made the note that repeated x's mean that the expression is not a function, but it's okay to have repeated y's. That's fine. You just can't have repeated x's and the thing be a function. So I'll say recall. I said for a function, there could be no repeated x values. And the vertical line test. Remember, we said that a function has to pass the vertical line test.
Which means a vertical line can't intersect the graph more than once.
You know, I've been doing all the writing for the past several videos. Why don't you do the writing today? It seems like you have a lot to say about inverses, so you go right on ahead.
Okay. Well, some new terminology. A function has no repeated x values. 1-to-1 means no repeated. Y'all want to guess? We've said a function has no repeated x values. Having said that, no repeated y values. Yeah. 1-to-1 means that there's no repeated y values. We had said that a slanted line is a function. You could draw a slanted line. Just drawing an XY. We had said that a slanted line is a function. Okay, there's no way you're going to have two ordered pairs with the same x value. But what about 1-to-1? Are there any repeated y values? Well, if we used a vertical line to test to decide if there's any repeated x values, follow the logic. See if you can figure out what am I about to say about a horizontal, I said it. About 1-to-1. To check for no repeated y values, you have a horizontal line test. A horizontal line test says if a horizontal line intersects a graph more than once, so 2, 3, 4 times, then that graph, I'll just say it, is not 1-to-1. Why would that be? Well, if you think about repeated y values, see this slanted line, it's just going to keep going down and up. it never turns around. The only way it could turn around, the only way you could have repeated y values is if it turned around. If it turned around like this, then, okay, it has repeated y's. But for just a slanted line, it never turns around. So,
What about a parabola opening upward?
yeah, that's a good question. So a slanted line is 1 to 1. What about a parabola opening upward? I'm just drawing a random parabola opening upward in red.
Look at those points where the graph intersects the x-axis. What are the y-coordinates of those points?
The y's. But the
Zero.
x, 0. Both of these y-coordinates are 0. Notice, right here,
It'd be a negative x. This one would have a negative x and a y value of 0. This one would have a positive x and a y value of 0. But either way, you have repeated y values.
And so wherever a horizontal line intersects a graph more than once, you have repeated y's. But notice, what about half a parabola? Would that be 1 to 1? Yes. If it were just half a parabola, then it'd be 1 to 1. Let's see, what are those first two homework problems?
Oh, let's see.
I believe you're going to be given a graph, and it's yes, no. It asks, is this 1 to 1? Oh, heck. Have we already answered that one? What is that? That's a slanted line. So, is it 1 to 1? Yeah.
Yes.
Okay.
Next.
Now, number 2, can you blow that up a little? Remember, sometimes one time a student told me, I can tell that thing's turning around.
You can't make that assumption.
Just look at what's drawn there. There's no arrows on it at all, really.
Right. So it's the domain is from -6 to what? About 2 1/3.
Uh-huh.
But so don't assume there are arrowheads anywhere. Is that 1 to 1? Yes, it will. It'll pass that horizontal line test. So yes, don't make the assumption, oh, it's going to turn around and start going back up. No, you don't know that. Only look at what's drawn. And there's no arrowheads, so it's not saying it's going to continue on. So what did y'all say? Yes, it is 1 to 1, or no, it isn't? Yes, it is 1 to 1. I agree.
So your natural question might be, well, wait, what isn't 1 to 1? Well, I showed you. A parabola opening up or
What
down.
about a circle?
No.
The graph circles.
Yeah.
It's not 1 to 1, but is it a function?
It's not a function.
Even a function.
Because a circle doesn't pass the vertical line test and it doesn't pass the horizontal line test. Okay? So,
Let's see.
let me see. I was going to define inverse.
Okay. Go ahead.
Right. The name of this is inverse function. So what the heck is an inverse? Well, in algebra, an inverse is formed by switching.
I say swap.
Oh, swapping. Oh, okay. The x and y values.
So you're just reversing the ordered pairs. Okay? You're just reversing the ordered pairs.
Now, if you look at problem 3, okay, yeah, to underline. Okay, let's look at number 3. This is another one that really, you don't have to, sometimes you have that scribble to get an answer. You got to do a lot of work to get it. This isn't one of them. This is where the work is up here. Look really closely. It asks, Decide whether the given functions are inverses.
And notice there are two functions, f of x and g of x. And they are functions. Notice there's no repeated x values on f. There's no repeated x values on g. They're functions, but are they inverses? Start reversing the ordered pairs. I'm going to start with the first function, 6, negative 5. If we reversed it, it'd become negative 5, 6. So the first row is okay. The second row, 3, 2. Reversing it, it became 2, 3. Okay, that's okay. What about the third row? Negative 6, 3 should become... Oh, so what's wrong here? They put that negative there, so no, these are not...
This is a little tricky, okay? Why is it no? Because they changed the sign on that 3. That 3 should have been a positive 3, negative 6. Okay? Let's see. Now
here they're written as ordered pairs. Are they inverses? Let's check. Negative 3, negative 5. Reverse it. Negative 5, negative 3. What about this ordered pair? Is that okay? Are these ordered pairs okay? The next ones? Yes, they reverse.
Is it clear what we're doing when we say, is this okay? Or we
1, 4, and the inverse becomes 4, 1. 4, negative 3 becomes negative 3, 4. 6, 9, is this okay?
9.
So, what is your answer? Are they inverses? Yes, they are.
I'll give you a word of warning. And you saw it on problem 3. What they'll do is change a sign to get a no, okay? So be careful. And you say, well, it's easy because if we miss it, we'll just do another one. Yeah, but on the test, if that problem's on the test.
Something I want to write.
Oh, okay.
Okay. We have a very nice notation for inverse, so we don't have to be writing out that word inverse. Let's suppose I'm going to make up two functions. Here's my function f. Let's say it's 0, 2, 1, 2, 2, 4, and 3, 6. There's a function f, and I'm going to skip a line. Here's my function g. I think you'll agree these are all functions. Let's see, I'll say 2 goes to 4, negative 2 goes to 4, 3 goes to 9, and 5 goes to 25. Okay, I've written out two functions, and notice they are both functions. In f, there's no repeated x values. In g, there's no repeated x values. So they're both functions. Let's form their inverses. We have a special notation for the inverse. Rather than writing out the word inverse, the notation is the name of the function and a little superscript of -1. Looks like an exponent, but it's not an exponent. If you see a function name with a little superscript of -1, that's our algebraic, that's our lazy way of saying the inverse of f.
Maybe draw a circle that little -1 and draw out and say inverse.
Inverse. That's not saying f to the -1 power. To form the inverse, we know all we do is just swap the ordered pairs. So 0, 2 becomes 2, 0. 1, 2 becomes 2, 1. 2, 4 becomes 4, 2. And 3, 6 become 6, 3. Let's form the inverse of g. What ordered pairs would we have here?
I'll get them going.
2, 4 becomes
4, 2.
4, 2, okay. I'm writing the inverses in red. -2, 4 becomes 4, -2. 3, 9 becomes 9, 3, and 5, 25 becomes 25, 5. Looking at these ordered pairs, we said that f is a function and g is a function. Are there inverses functions? Look at f inverse. I think right off there's something wrong with it. What is it? Remember, to be a function, there can't be a repeated x value. Here we have repeated x values, so f inverse is not a function. What about g inverse? I guess I shouldn't have had the problems be the very first two ordered pairs. Look, we have repeated x values. The point I'm trying to make is that it's fine to have repeated y values in a function, but if you do, then when you form the inverse, the repeated y's are going to become repeated x's. So go back to that one that we just did that made me start thinking about these things. No, that's not it. Where is it? We said on number 4, we said those functions are inverses. Notice f, when you form that inverse, in order for the inverse to be a function, you have to have a one-to-one function to start off with. You can't have repeated y's in the original function. If you have repeated y's in the original function, that's what I was showing here, or trying to show. If you have repeated y's in the original, they become repeated x's in the new function. Repeated y's in the original become repeated x's in the new function. So we want to make a note. Oh, by the way, these things, f and g, they're not functions.
F inverse.
F inverse and g inverse are not functions. Only one-to-one functions can have inverses that are functions, and that's important because all they're going to want us to do is to find the inverse if it's a function. If it's not a function, then they're not interested in the inverse. So let's make a note. Only one-to-one functions have inverses that are functions. So from here on in, when they're wanting you to find an inverse, they're going to say, if it's not one-to-one, then they don't just say that it's not one-to-one. They don't want you to find the inverse. To illustrate, looking at number 5. If the following defines a one-to-one function, find its inverse. If not, write not one-to-one. So before we do anything, we need to decide, is this original function one-to-one? You look at the y coordinates. Are there any repeated y values in that original function? No. So it is one-to-one. In that event, they want us to find the inverse. So 1912 would become 1219. 810 would become 10:8. It looks to me like it's which one? The negative 11, negative 20 becomes negative 20, negative 11. I think that's response A.
So when it says, if it's one-to-one, find its inverse, it's saying, if there's no repeated y values, switch them. Switch the x and y's. That's what it's saying. If there's no repeated y values, switch it. Number 6 is another one like that.
Okay, hold on. Okay, looking at number 6, it's the same instructions. If it's one-to-one, find the inverse. If it's not one-to-one, just say it's not one-to-one. Is this one one-to-one? What's wrong with it? Okay, there's two negative 15s as y coordinates. There and there. Negative 15 is being repeated, so you'd select not one-to-one.
What do y'all think the common wrong answer is? I remember years ago having a class which I must have done a very poor job because every student in the class missed this problem. Why do you think they chose as the right answer?
And you reversed the ordered pairs. I think it was B, the one.
Yeah, they chose B as the wrong answer. Do you see why B is not the right answer? They chose B as the right answer, but B is wrong. Why? It didn't just say find the inverse. It says
if it's 1 to 1, find the inverse. If it's not 1 to 1, say not 1 to 1. They're not going to have you find inverses that are not functions. They're only concerned about it. Although we can find an inverse. We can find inverses that aren't functions. I found inverses that weren't functions right here in my little made-up.
Tim, though, it's called inverse functions, not just inverses. Since we're really only interested in, inverses that are functions.
Oh, here's another one.
Same instructions. A, B, C, or D. Which one is it going to be?
Let's decide. What do y'all think? Is it 1 to 1? Look at the y coordinates. Are there any repeated y coordinates?
You know what?
I'm going to write it out.
Okay, write that one out.
Let me write the problem down first.
-3, 3, 21, -27, -7, -9, and -2, 6.
Okay, there's our function. First thing we have to do is decide, is it 1 to 1, and what's our conclusion? Yes, it is 1 to 1. There's no repeated y's.
No repeated y's.
No repeated y values. Here's my thoughts. There's no repeated y values, so it is 1 to 1. Now we reverse the ordered pairs to find the inverse. -3, 3 becomes 3, -3, okay. 21, -27 becomes
-27, 21.
Reverse the third ordered pair. -9, -7. Reverse the fourth ordered pair. 6, -2. So A, B, C, or D.
It's definitely not D. Oh, I think just by looking at the very first one, I can assume it is A. Is that it? Looks like, oh, by the way, looking at this, it looks like you just wrote down the problem and pretty much wrote the answer. This is one of these problems that there's work up here, not a lot of work on the paper, though. Let's see if the next one is something like this. Oh,
okay.
Oh, this is a neat question, neat problem.
Let's come back over here to this number 7. Let's consider the above function and the inverse. Consider the above functions. And for lack of anything, a name, I'm going to label this first function that I'm working with, number 7 here. Okay. I'm looking here, and I'm going to name this F. F equals. That's my function F.
So how will you denote the inverse of F on the red one?
I'm going to use that little superscript notation that looks to the naked eye like it's saying F to the -1 power. But when you see a function with that little -1 in the exponent position, that's our algebraic way of saying the inverse. That means the ordered pairs have been reversed. First thing I want to do, I want to know the domain of F. I want to write out the domain of F. Which numbers are in the domain of F? The domain is what? The x values or the y values? The x, so -3, 21, -7, And there's another number in the domain. What is it? -2. I agree. Let's write out the range of f. What numbers are in the range of this first function? 3, okay. What else? -27, I agree. We're writing out the y values. -9 and 6, I agree. The domain of f, that's the set of all x values. The range of f, that's the set of all y values. Now, let's find the domain and range of the inverses. What numbers are in the domain of the new function, f inverse? Which numbers are in the domain? Which numbers are in the domain? Give me one of them. Give me the first one. 3. What else? -27. What else? -9 and 6. Realize the way we're swapping the x's and y's. This should be obvious to you that the domain of the inverse has to be the range of the original function. This is saying the y's in the original will equal the x's in the new function.
Y became an x.
The y became an x in the inverse. Let's apply that same logic to the range of the inverse. The numbers that are y values in the new function, where do they start off? The x's in the original. Notice -3, 21, -7, and -2. The domain of the original is equal to the range of the new one.
So if you want to say something algebraically, the domain of f is the range of f inverse, the range of f is the domain of f inverse, and it should be obvious why. X becomes y, the y becomes x. Are we ready to do that problem?
Yes.
How would y'all complete this? The domain of f is equal to the blank of f inverse, and it gives you a choice. What should I choose there? Range. That's saying the x's became y's. Now the range of f is equal to the blank of f inverse. So the y's became
x's domain.
And this is one of those things for everyone's number 8 that doesn't regenerate. There's no other way it could regenerate. Oops, what am I doing? Any questions on that? Domain of f is equal to the range of f inverse. Range of f is domain of f inverse. Okay. Let me
go on to that next one. Okay, if a function f has an inverse, and by that they mean it has an inverse that's a function, and f of -3 is equal to 6. Hold on, let me write this down. F of -3 is equal to 6. They want us to find f inverse of 6.
What do y'all think? Easy or hard?
Okay, first of all, switch over. When we started functions, I made the point that functions are just ordered pair generators when they're written as equations. A function written as an equation with variables is just generating ordered pairs. The number in the parentheses is x. The value of the function is y. So if I wrote this information as an ordered pair, when the x coordinate is -3, what's the y coordinate? 6. Now let's find the inverse. We know how to find an inverse. You reverse the ordered pairs. That 6 becomes the x value, and -3 becomes the y value. So when x is 6 in the inverse function, when x is 6, What's the y value? -3. Notice using function notation how the x became the y became the x. And that's not surprising because that's what an inverse does. It reverses the x and y notation. Any questions there?
Would y'all have just guessed -3 just because there's no other number there?
Because the functions are inverses of each other. Input of the function is the output of the inverse, and the output of the function is the input of its
that
inverse.
explains it all.
In the 90s, they decided that we're engaged in abstract thought here. You understand that. There are no functions floating around. On your way home today, you're not going to see a function out your car window and decide to pull over and find its inverse. This is abstract thought, okay?
Math is the only pure abstract science.
After applications are found, but only after the math is discovered. Once the math is discovered, it's that topology and dynamic systems that Tony and I were working on in our master's program 30-something years ago, okay? But now, oh yeah, it's got plenty of applications, important applications. There were none back then, okay? And so, but I remember something.
That math is abstract. I want you to think about one thing. Choose a number.
3.
No, you might do this. 47. Define 47 without using any other number. If a Martian came to Earth and said, "What is this, 47?" Well, you might show him $47.
I think it'd be easier to do something like 3. You could show him this. No, these are fingers. This isn't 3. These are just fingers.
You could show them $3, but
that's dollars. That's not 3. 3 itself
the numbers
isn't.
are abstract.
But I remember in the 90s they decided, they're going to make math more
less abstract.
They introduced all these little function machines in the books. They'd have I'm serious. They'd have little pictures drawn, and the X would go into the little machine, and you see all these little gears, and guess what would drop out? It'd go into the function, and the X would drop out and turn into what? A Y. And that was tangible and realistic because, and I remember saying, this is crap. There are no function machines. Okay, there's no diagram on the book, but we need to understand this is all just abstract thought, okay? You're not going to run into any functions on your way home, what have you. But that input and output, that's a carryover from back when they decided they were going to make math more concrete and realistic. We'll make it like machines with inputs and outputs as if it's an assembly line. Another failed attempt to make something that's abstract into something concrete and not abstract. I've been doing this long enough. There's other instances I can use where I need to talk some more now.
Okay. 10, 11. You know what? We've actually seen the two inverses cancel each other out. Like if you took a number and multiplied it by 3, 1 would go to 3, 2 to 6, 3 to 9, 4 to 12. The inverse would reverse those ordered pairs. So it would be 3, 1, 6, 2. So the inverse of multiplying by 3 would be what? Dividing by 3. Okay? If you do a function and its inverse, they cancel each other out. We've seen some stuff. Did you want to mention this?
Yeah, I remember this stuff from composition of functions. Last week we were looking at it, if I remember correctly. We found the composition. We'd go through the two, we performed the functions consecutively in either order, and everything canceled out except the variable x. That's basically the algebraic definition of inverse. We already know what an inverse does. An inverse takes the ordered pairs, the x becomes the y becomes x. But how do we say that algebraically in terms of functions? Here's our definition, our formal definition of inverse function. Let's assume f and g are one-to-one functions. F and g are inverses if each of the following is true. F and g are inverses if each of the following are true. The first one, there are two conditions. If you find f composed with the g of x, that has to reduce to x for every x in the domain of g. And if you reverse that order, let's say, I'll keep using blue, g composed with f of x, that must also reduce to x for every x in the domain of f. If you find their compositions in both directions and everything cancels out except an x, then you know those functions are inverses. And that's what we have here. Okay, that's what we had here. F composed with g of x, it reduced to x, and then we reverse the order, and it also reduced to x. How is that saying it's the same thing as, that's algebraically saying the same thing as swap the ordered pairs? How is that possible? Well, because I don't think it's immediately obvious that this is saying swap the ordered pairs, is it? I don't think so. Let's consider the following functions. I have two functions I want to look at. Here's the first one. F takes 1 to 3 and 2 to 4. And do you agree that's 1 to 1? Each x value is assigned to one and only one y value, and there's no repeated y's. Each y value has only one and only one x values. So the inverse would have to be what? If we were going to form the inverse of these, f takes 1 to 3, the inverse would have to take 3 back to 1, and 4 would have to go back to 2, based on our intuitive understanding of inverses. Okay. This definition says that if you perform the two functions consecutively in either order, you're going to end up wherever you started. So let's start at 2. Perform the two functions. 2 goes to 4, 4 goes back to 2. The only way that can happen is if the ordered pairs are just being reversed. Say you start at 3. 3 goes to 1. 1 goes back to 3. The only way these two things, you can end up where you started, the only way that's going to happen is if the ordered pairs are just reversed. So these things are inverses. Suppose I'm going to make up another 2. 1, 2, 3, 4. Let's suppose that f takes 1 to 3 and 2 to 4. So the red function is f. Now the green function. we'll take 3 to 2 and 4 to 1. With our intuitive understanding of inverses, I think we'll agree these are not inverses because they're not reversing the ordered pairs. 1, 3, it should go back to 3, 1 if they're inverses. But this definition says, are you going to end up where you started? Let's start at 1 and perform the two functions. 1 goes to 3, 3 goes to 2. You didn't end where you started. If you started at 4, 4 goes to 1, 1 goes to 3. You're not ending where you started. The only way you're always going to end up where you started is if the ordered pairs are just swapped. The only way that's going to happen is if the ordered pairs are swapped. These things here, clearly not inverses. And to remind you of what you were doing there when we were looking at composition, they have a problem here in the homework where they want you to use this definition to decide if the functions are inverses. If you find their composition in both directions and everything cancels out except for x in both directions, then you know they're inverses. If you're left with something other than an x, they're not inverses. Let's look at number, is it 10?
See, here we had 2.
Oh, yeah, there was and that other homework assignment from last week, here was 2 of them. I mean, we looked at number 11 a moment ago. Here's number 10. Do y'all remember that? The composite, it's sort of hard to tell what's going on with all these circles and arrows and stuff. It's a little busy, doesn't it? But it reduced down to x. And remember, they'd ask you, does f composed with g of x equal g composed with f of x? They were trying to prepare you for this definition. So,
the little arrows, I wanted to show something. When we did that,
why don't you take over? I was going to have you take
over. It's not because, I'm just answering text messages. It's like the other day I sat here while he was working, trying to find something to show y'all, and then I forgot. And it had to do, when we were doing this one, this stuff here, to find f of g of x, it means plug g into f, but sometimes function composition isn't written as fog and golf. It's written just with a lot of parentheses like this. Plug g into f, plug f into g. Looking at this little thing here. Okay, so f is pizza, g is pineapple. This f of g, that's fog x. That means plug g onto f. You're putting pineapple on the pizza. Okay?
So you have pineapple pizza.
But here, you're putting pizza onto pineapple. So there's a slice of pineapple with little bitty slices of pizza on top of it. And I'll mention this just because one day a student came up to me, and it's a friend of mine, sent this to me, said, I don't get it. I have a friend that's an engineer, and several of them, and they had this, and they were laughing at it. They posted it on, I don't remember, it was their Facebook or Twitter, and laughing at it, and he didn't get it. And he wanted, what does it mean? And I was like, oh, you remember fog and golf, from way, he remembered that. He didn't remember ever doing inverse functions or composition of functions, but he remembered the crazy teacher that talked about fog and golf. Okay, put pineapple on pizza, or are you putting pizza on pineapple? I like that little thing. You may not find it funny or amusing, but I do. God help me. Oh, gosh, wow. Okay, now, what does that have to do with anything? Well, let's do number 10.
If y'all don't see the significance of it, join the club. Okay?
Oh, 10. You should be ashamed of yourself.
I do get it. I do get it.
I don't think you do, because you don't even get the arrows of how you do it with the arrows.
I do.
Okay, so problem number 10 says, decide if these are inverses of each other. Well, what you're going to do is look at f of g of x and g of f of x. Look at fog and golf. If both of them equal x, then, yeah, they're inverses. If one of them, just one of them, doesn't equal x, you can stop and say not inverses.
And remember, basically, for it to equal x, everything has to cancel out except for the variable x. So let's see. This is a good problem to remind you of composition of functions. F of x is the fraction 5 over x minus 6. G of x is the fraction with 5 on top and x on the bottom. And then there's a plus 6.
Okay, so I've written it down. So we're going to first find f of g of x, or fog x. That means plug.
Okay, do y'all remember what's on the outside? Which function's the outside function for fog x? F is on the outside. So you're going to plug G of x into F.
So some of that circling of mine, I'm going to put all of this right up here. Ooh, it's going to be sort of messy. I have a black.
Why do you think I switched?
Oh, okay. Well, black 5, and then I still have the black minus 6. But instead of this black x, I'm going to put this circled. Oh, gosh. 5 over x plus 6.
You see, I was looking at the next problem as Tony was carrying on about pineapple pizza. And so, that's why I was like, okay, Tony, you do this one. Something's going to start canceling out real fast here.
What cancels out immediately?
The 6
minus 6. So let me write it out without the 6 minus 6. We have a 5 on top, and then a blue 5 over x on the bottom.
Lily, I found we do have a pencil. If you'd rather had a pencil, I do have a pencil.
Oh, wow, that's going to live in YouTube history. Tim asking Lily, would you rather have a pencil? Huh.
Okay. Well, the 6's are gone. Now we have something called a compound fraction. That's a fraction that contains one or more additional fractions, and there are a variety of methods of simplifying these things. What I like to do, some people like to write it as division and then multiply by the reciprocal. I like to multiply. I introduce some terminology. The major fraction bar. Show them what the major fraction bar is.
This is the major fraction bar.
And the subsequent fractions that appear within the fraction, I call those fraction bars the minor fraction bar. And what I do is I multiply, if I have a fraction of this form, I multiply above and below by the minor denominator.
The minor denominator would be just this blue x right here. When he says multiply above and below, he means above and below the main one. If I multiplied above and below by x,
what's about to happen? Well, on top I have a 5x. Okay, nothing to cancel there. On top I have a 5x. But what's about to cancel in the bottom?
Can I cross cancel these x's here? Well, let me reword that. I can. And by doing that, can I now cancel the 5s?
Write it out. 5x over 5. That's what you have there, Tony.
Oh, okay. I was just
5x
over 5. And now I can cancel the 5. And what am I going to get? X. At this point, you have about an 85% chance that...
In most cases, if one composition reduces to x, the other one will also. So odds favor, yes, these things are functions. But this isn't a gambling class. We're not betting. We're going to go through and find g composed with f of x. See, does that cancel out to just x also? And it's some good algebra simplifying these compound fractions.
Oh gosh. I didn't. So this g of f of x, that means plug f into g. Oh gosh. So in place of this blue X, I'm going to put all of this stuff here. So I have the blue 5 over. And in place of that blue X, I'm writing 5 over X minus 6.
Does he have something else there?
The plus 6. I should have written that right off, probably.
So he's replacing that X.
You see, right, it might be
X.
tempting, let's cancel the 5s. But wait a minute, you can't really just cancel the 5, because then you're going to have what? Nothing here, nothing there. I guess a 1 maybe. But you're still going to have all these fraction bars. So let's do that little trick that Tim said. Multiply above and below.
What would be the minor denominator? Tell me, looking at this fraction right here, what are we going to have to multiply above and below by? It's a little messier. Up here it was just a letter X. What are we going to multiply above and below by here to cancel that denominator? X minus 6, that's right. And resist the urge to start distributing. Looking at the major denominator, this thing, all of that stuff right there. Something down here is about to cancel out. What is it? The X minus 6. It's okay, there and there. So don't distribute the 5 over the X minus 6. Remember, you're trying to cancel. This is already factored here. 5 times X minus 6, it's already factored.
Would y'all cancel the 5?
I would write it out all. I'd write the 5 times X minus 6 all over 5.
I'm going to just write X minus 6.
Oh, okay.
Plus 6.
Did y'all follow the way he canceled the 5s? Once he canceled the X minus 6s, he had a 5 on top and a 5 on the bottom that he could cancel out.
Okay, I'll write it like that. 5.
No, you got to have the parentheses X minus 6.
See, once I canceled the X minus 6 here and here,
he had this left.
5s.
He canceled the 5s.
But I think most students would just do what I did here. Just cancel the 5 and cancel the X minus 6.
But I thought that we were trying to make sure they saw what was happening.
Yeah, you're right.
Doing what most students do.
And so
Any questions there?
So what are we going to answer? Are these two things functions?
Did they both reduce to X? Say yes. Okay. So yes, they are functions.
F and G are functions.
Okay.
That's the formal definition of inverse. The informal is you switch X and Y. The formal is fog X equals X, golf X equals X.
So the next sensible question, we know if you give me two functions, or say I'm driving home and I notice a couple of functions laying by the roadside or something, I could take those functions and figure out if they're inverses.
By looking at fog X and golf X.
Okay. Well, so the next sensible question is, suppose you have one function. How do you find the inverse? How did they find these two functions that were, they had one and then they got the inverse. How did they go about doing that? In order to find inverses, we're not going to find inverses unless the functions are one-to-one. So I want to discuss a little bit more about one-to-oneness before I write out how you find an inverse. Remember, for one-to-one functions, we work with functions in 3 different ways. We work with them just with ordered pairs, the lists of ordered pairs. It's easy. If the function is just a list of ordered pairs, it's easy to decide if they're one-to-one. Just look at the y values. Are there any repeated y values? So with ordered pairs, this is for an ordered pair function, you know there's no repeated y values. For a graph, it's easy to decide whether a function's one-to-one. If it's a graph, use that horizontal line test. the third method of representing a function, the one that we use primarily, an algebraic equation. How do you tell if an algebraic equation is one-to-one? So the third method, algebraic equation. We don't want repeated y values. We don't want repeated y values. So let's see. There was a little picture Tony drew. Here's one right here. This function right here, it was not one-to-one. Do you agree? Remember, it was a parabola opening upward. Here you had a negative x and 0 for y. Here you had a positive x and 0 for y. So you had two different ordered pairs with the same y coordinate. What are the equations? This is a parabola. What term has to appear in the equation of a parabola?
What's the biggest exponent?
What's the biggest exponent? We said this was a quadratic function. When we first started graphing these, what has to appear in the equation for it to be quadratic?
Ax
what? Ax
squared?
It's those even exponents that cause problems. If you have an even exponent, whether it's an x squared or an x to the fourth, it doesn't matter if you plug in a positive 5 or a negative 5. When you square it, when you raise it to that even exponent, that's going to give you the same number as it would if you started with a negative x value. It's those even exponents that cause problems. Even exponent,
not one-to-one.
not one-to-one.
Because when you square a negative, you get the same thing as when you square a positive. You wind up with these repeated y values. Are you going to go back over there?
Yes, but I was just thinking
chart?
there was another graph. There was another graph that was it wasn't a smooth U, okay? We said that you can't have even exponents. If your equation has even exponents, then you should expect to get repeated y values.
So U's, but we graphed one or two V's.
What were those V's?
Do you remember, when did you have a V?
Let's see.
As if you had, I'll give it to you.
Wait. No even exponents. If it's an algebraic equation and it's one-to-one, they can't have even exponents. Like, you don't expect there to be x squares, x to the fourth. Even exponents take negative quantities and make them the same as the positive quantity. There's something else there'd be negatives on the inside, but then you do this little thing and they become positive. Had a V-shaped figure.
Just say it.
Maybe absolute value functions, you don't expect them to be one-to-one. So if you have an algebraic equation that's a function, in order for it to be one-to-one, there should be no even exponents. There shouldn't be any absolute values. No absolute values.
So this is an easy way to look at an equation and say,
with a high degree of certainty, I could rig one with an even exponent that is not one-to-one, okay? I could do that. But it have to be rigged very carefully. Generally, you don't expect one-to-one functions to have even exponents. You don't expect one-to-one functions to have absolute value symbols appearing. So,
on this one here.
Oh, yeah, look at this one. Both of those are one-to-one. They found the inverses. They gave them to us. But do you see, I could do one little thing. Say right here, where there's that x, I could write one little tiny thing right up there above that x, and then it wouldn't be one-to-one. I could write a square. If that had been x squared minus 6, then it didn't matter whether you plugged in a positive 1 for x or a negative 1 for x. You're going to get the same y value. Looking over Are there some other equations? Let's see.
Nope, I don't think we have other equations.
No, okay, we don't.
Well, like number 11. Let's look at number 11 and tell me, is it 1 to 1?
What do y'all think? Is this function 1 to 1? If it's 1 to 1, they want us to find a formula for its inverse. But if it's not 1 to 1, I haven't written out that recipe yet. But
how would y'all answer this question?
Is it 1 to 1? Yes, I agree. You can do something like, to convince yourself, plug in positive 1 and negative 1. If you plug in a positive 1 for x, do you get the same thing you do if you plug in a negative 1? No. So, yes, this thing is 1 to 1.
If there's no absolute value bars and no even exponents, 1 to 1. So how do we find that 1 to 1? Find the formula for that 1 to 1. That's what he's going to do.
And it's not as bad as you think, okay?
It's pretty easy to find the inverse for
to
equation.
Find F inverse. The first thing you got to do, verify that the function is 1 to 1. Make sure F is 1 to 1, because if it's not 1 to 1, they don't want you to find the inverse. They want you just to say not 1 to 1. So I'll say verify. Really, you're just convincing yourself. Verify that F is 1 to 1.
Why not? You're right.
I'm going to do that. All right. No even exponents. No absolute values.
Now, notice he's saying no even exponents. Like x cubed, that's fine. An odd exponent is fine. No,
because odd exponents don't take negative quantities and change them to positive quantities. That's the whole problem here. That's been the source. That was the problem with those. That's why we ran into those complex numbers, because it goes back to the way that when you take a negative and you square it, it gives you a positive, okay? Even exponents change the sign on the result. So now, second step. Swap x and y. Isn't that what an inverse does? You swap x and y. And at that point you have an equation that's a form of the inverse, but they're going to want you to get it so that you can use the F inverse notation. So once you swap x and y, you're going to have to solve for y. And once you solve for y, you can then replace y with F inverse of x. Well, my lab will do that for you. They'll type the F inverse of x equals, and then they'll have a little blank for you to type in the inverse. So really it's just a 3-step process. Once you solve for y, the inverse is the step on the other side of y.
I remember when I was a graduate student, I don't know if you were in on this conversation, I was tutoring some teachers, some other teachers' algebra students, and I noticed that this elderly teacher, in her algebra class, she didn't tell them to find F inverse x. She had them write an equation for the inverse. So all they had to do was the first 2 steps. And I remember speaking to my graduate advisor, why isn't she telling them to find F inverse? And she said, prior to the 50s, they didn't do that. The books just said, find an equation. All they had to do was swap x and y, and they were finished. But then coming up after the 50s, all the books started using this notation about the F inverse. And I remember her name, Miss Shepherd. She never adopted that. Okay, she'd been doing it long enough. But, so another little interesting thing, back in the day, they didn't find F inverse. They just wrote an equation. So here's our function.
Just like back in the day, we didn't use interval notation for every inequality we did. So, number 11. Okay.
We've already decided that it's 1 to 1. There's no even exponents. There's no absolute value bars. So now we're going to go through those steps to find a little formula for the inverse.
And notice how they have that. F inverse of x equals. That's why I was saying this fourth step you really don't have to do. Once you solve the y, the thing on the other side is going to be what you write in the box. So this is really just a 3-step process. And we've already said no even exponents, no absolute values, so f is 1 to 1. I'm going to number the steps. Since this is the first inverse we found for an algebraic equation, I'm going to number the steps. Okay, f is 1 to 1. So we did that. Second step.
Swap your x and
Swap
y.
it x and y. Wait a minute. I don't see a y here. There's a big problem. I see the letter x, but I don't see that letter y. What's taking the place of y? There's something here that's acting like the letter y. What is it?
Just the f of
F of x is just a fancy way of saying y. So you're thinking to yourself, there, that's y. F of x is the y. So you're going to swap x and y. So I'm going to do it in green. Y is going to become x. That x is going to become y. F of x is a fancy way of saying y. So when we're swapping x and y, f of x was y, it became x, the x became y. The third step, solve for y. That means we need it in the form y equals. We can't keep y down there in the denominator. We need to get y out of that denominator. What do you think? What can we do to get y out of that denominator? You know what? I remember multiplying both sides by the least common denominator. But look at this. I could write this as a proportion. One fraction equals another fraction. We had a little shortcut method to get rid of those fractions when we had a proportion. When we had a fraction equals a fraction. Who remembers what that little shortcut method was? What would we do? I'll give you a hint. Maybe I do. Maybe this x will remind you. That little cross that I just wrote there. Cross multiplying. You take the x times the y plus 8. Well, what are we going to have to do if you take x times y plus 8? And I'll write it out. X times y plus 8 is equal to 7 times 1. Since y'all are being so quiet, I'm afraid I'm losing you, so I'm going to show that multiplication. And 7 times 1, we know that that's a 7. What are we going to have to do here? To get distribute. So x times y becomes xy plus, here, 8x, I agree. We're trying to solve for y. We're trying to solve for y. We knew we had to get it out of the denominator. It's out of the denominator. So I want that y isolated. There's really only one correct next step. What is it? What are we going to do? We want the y term by itself. I couldn't hear you. Subtract the 8x, I agree. Subtract the 8x. So we're going to have xy equals 7 minus 8x.
Or negative 8x.
Or you could put negative 8x plus 7. Now we want to get rid of that x. X times y. What are we going to do? Divide by x. Divide by x. So the x's cancel.
Here.
That x here. So we have y equals 7 minus 8x all over x.
Don't cancel the x and say 7 minus 8.
You can only cancel the x's as if you split up. Remember 7 over x and then the 8x over x. But my lab takes it like this,
And I prefer it like
and I
that.
prefer it like that too. So I'm going to stop right there. Any questions?
And so now the y is acting like f inverse. So what you're going to type in is what he just circled.
Oh, I was numbering the steps. So here's step 3, solving for y. That's what we were doing down to here. And so step 4, replace the y with f inverse of x. But it seems to me like that's unnecessary for us. The program does that for you. It replaces the y. You solve for y, the thing on the other side of y, that's what you're going to type in.
So 7 minus 8x all over x. Fraction. 7 minus 8x all over x.
Any questions there?
So here's a function, and there's its inverse, written as little formulas. Right?
Let's do another one.
This is the last one, number 12. Number 13 is a circle problem. 14 and 15 are cut point problems. So this is the last new stuff.
Determine whether the function is 1-to-1. If it is, find a formula for its inverse. F of x is equal to x cubed minus 4. Before we start our work on this, what do you think? Is this function 1-to-1? Yes? Well, wait a minute. I see an exponent. I see an exponent right here. It's not an even number. It's an odd number. If you plug in a -1 for x, you're going to get a -1. If you plug in a +1 for x, you get a +1. Odd exponents don't change negative quantities to positive quantities. So yes, this thing is 1-to-1.
Now,
so let's switch
it
over.
over because you're going to have to go through those steps.
We've already said f is 1-to-1. Okay, we convinced ourselves of that very quickly. Now we're going to swap x and y. We're going to swap x and y.
Keep in mind that f of x is
actually what? Y. So x equals y cubed minus 4. So we've done the first 2 steps. We convinced ourselves that f was 1-to-1. We swapped x and y. Third step, solve for y. We need that y by itself. Well, I know what I could do to get rid of that -4. What could I do? Add 4, so I'll have x plus 4 is equal to y cubed. But now I need to get rid of that cube. What undoes the cubing function? The cube root. Realize what you've just done. You've just now said that the inverse of the cubed function is the cube root function. That's what's happening here. We're using an inverse to find another inverse function. You're performing these 2 things consecutively. When you perform the cube and the cube root consecutively in either order, they cancel each other out. That's the definition of an inverse function. The cube root and the cube cancel each other out, leaving you just y equals the cube root of x plus 4. So what are you going to type in your box? That cube root of x plus 4. There's no need to replace the y with f inverse of x.
Because they've already done that.
They've already done that for you here.
Cube root of x plus 4. Click there, and here's my little cube root symbol.
Is this the first time we've used the cube root hot button or the nth root? Notice it has that little blue box for an index. And so you type in the 3, then you click there, and we have what's under there, x plus 4.
Any questions? A nice little assignment dealing with functions. So, any questions that you want recorded?
Okay, I'm going to